Welcome back to a new session of the MOOC on Information Security. Today we will discuss Message Digest. While learning digital signature, we have already mentioned that a message digest is a fixed size numeric representation of the contents of a message computed by a hash function. A message digest can be encrypted, forming a digital signature. Messages are naturally variable in size, but a message digest is a fixed size numeric representation of the contents of the message. Usually, a hash function is used to compute the message digest, which is a transformation that meets two criteria. The hash function must be one-way. It must not be possible to reverse the function to find the message corresponding to a particular message digest other than by testing all possible messages. And it must be computationally infeasible to find two messages that hash to the same digest. The message digest is sent with the message itself. The receiver can generate a digest for the message and compare it with the digest of the sender. The integrity of the message is verified when the two message digests are the same. Any tampering with the message during transmission outcomes in a different message digest. A message digest created using a secret symmetric key is known as a message authentication code or MAC because it can provide assurance that the message has not been modified. The sender can also generate a message digest and then encrypt the digest using the private key of an asymmetric key pair, forming a digital signature. The signature must then be decrypted by the receiver before comparing it with a locally generated digest. Message digest is used to ensure the integrity of a message transmitted over an insecure channel where the content of the message can be changed. The message is passed through a cryptographic hash function. This function creates a compressed image of the message called digest. Let us assume Alice sent a message and digest pair to Bob. To check the integrity of the message, Bob runs the cryptographic hash function on the received message and gets a new digest. Now, Bob will compare the new digest and the digest sent by Alice. If both are same, then Bob is sure that the original message is not changed. This message and digest pair is equivalent to a physical document and fingerprint of a person on that document. Unlike the physical document and the fingerprint, the message and the digest can be sent separately. Most importantly, the digest should be unchanged during the transmission. The cryptographic hash function is a one-way function, that is, a function which is practically infeasible to invert. This cryptographic hash function takes a message of a variable length as input and creates a digest or hash or fingerprint of fixed length, which is used to verify the integrity of the message. Message digest ensures the integrity of the document. To provide authenticity of the message, digest is encrypted with sender's private key. Now, this digest is called digital signature, which can be only decrypted by the receiver who has sender's public key. Now, the receiver can authenticate the sender and also verify the integrity of the sent message. The hash algorithm MD5 is widely used to check the integrity of messages. MD5 divides the message into blocks of 512 bits and creates a 128-bit digest, typically 32 hexadecimal digits. It is no longer considered reliable for use as researchers have demonstrated techniques capable of easily generating MD5 collisions on commercial computers. The weaknesses of MD5 have been exploited by the Flame malware in 2012. In response to the insecurities of MD5 hash algorithms, the Secure Hash Algorithm or SHA was invented. Uses of message digest functions. Message digest functions are widely used today for a number of reasons. Some of those reasons are: message digest functions are much faster to calculate than traditional symmetric key cryptography functions, but appear to share many of their strong cryptographic properties. There are no patent restrictions on any message digest functions that are currently in use. Message digest functions appear to provide an excellent means of spreading the randomness from an input among all of the function's output bits, which means diffusion. Using a message digest, you can easily transform a typed passphrase to an encryption key for use with a symmetric cipher. Message digest can be readily used for message authentication codes that use a shared secret between two parties to prove that a message is authentic. Marks are appended to the end of the message to be verified. Because of their properties, message digest functions are also an important part of many cryptographic systems in use today. Message digests are the basis of most digital signature standards. Instead of signing the entire document, most digital signature standards specify that the message digest of the document to be calculated. It is the message digest rather than the entire document that is actually signed. MACs based on message digest provide the cryptographic security for most of the Internet's routing protocols. Programs such as PGP use message digest to transform a passphrase provided by a user into an encryption key that is used for symmetric encryption. Attacks of message digest functions. There are two kinds of attacks on message digest functions. The first type is finding two messages that have the same message digest. The second attack is considerably harder. Given a particular message, the attacker finds a second message that has the same message digest code. MD5 is probably secure enough to be used even though it is possible to find MD5 collisions, and it will be very difficult to transform this knowledge into a general purpose attack on SSL. Now, we'll discuss the message digest algorithm, though we have mentioned it at the time of hash functions. MD5 or message digest algorithm. A one-way cryptographic function that accepts a message of any length as input and returns as output a fixed length digest value is known as the MD5 hashing algorithm. It is used for authenticating the original message. However, it was originally designed for use as a secure cryptographic hash algorithm for authenticating digital signatures. It has been deprecated for use other than as a non-cryptographic checksum to verify data integrity and detect unintentional data corruption. We have seen the characteristics, working and uses of MD5 in our previous session. So, here we will go through its use as a checksum. Cyclic redundancy checks or CRC codes are often suggested as possible substitutions for MD5 because both MD5 and CRC perform hashing functions and both deliver checksums. A 32-bit CRC code is used to detect errors during data transmissions, so corrupted or lost data can be identified. Meanwhile, MD5 is a secure hash algorithm and a cryptographic hash function that can detect some data corruption but is primarily intended for the secure encryption of data that is being transmitted and the verification of digital certificates. MD5 follows the Damgard-Merkle iterative structure, where the hash is computed by a repeated application of a compression function to successive blocks of the message given in the following figure. A schematic diagram of Damgard-Merkle iterative structure is shown here. For MD5, the compression function takes two inputs, a 128-bit chaining value and a 512-bit message block, and produces as output a new 128-bit chaining value, which is the input to the next iteration of the compression function. The message to be hashed is first padded to a multiple of 512 bits and then divided into sequences of 512-bit message blocks. Then the compression function is rapidly applied, starting with an initial chaining value and the first message block and continuing with each new chaining value and successive message blocks. After the last message block has been processed, the final chaining value is then passed to the output as the hash of the message. Because of the iterative design, it is possible from only the hash of a message to compute the hash of longer messages that start with the initial message and include the padding required for the initial message to reach a multiple of 512 bits. Padding data helps to add random bytes to our data so that it is more difficult for a prospective attacker to find which bytes are the actual data. Padding also allows us to put our data into blocks so that we can operate on pieces of data that are of the same size. Applying this to the prefix approach, it follows that from MD5 KM, where K is the key and M is the message, one can compute MD5 KM dash for any message dash that start with message P, where P is the padding on KM. In other words, from the message authentication code of MPX for any X, without even knowing the key K and without breaking MD5 in any sense. This is called a message extension or padding attack. So, a message digest is a fixed size numeric representation of the contents of a message, computed by a hash function. A message digest can be encrypted, forming a digital signature. The message digest is sent with the message itself. The receiver can generate a digest for the message and compare it with the digest of the sender. The integrity of the message is verified when the two message digests are the same. Any tampering with the message during transmission almost certainly results in a different message digest. A message digest created using a secret symmetric key is known as a message authentication code or MAC because it can provide assurance that the message has not been modified. The sender can also generate a message digest and then encrypt the digest using the private key of an asymmetric key pair, forming a digital signature. The signature must then be decrypted by the receiver before comparing it with a locally generated digest. Hope you are clear about the message digest discussed here. See you next time. Bye.